So you found the skeleton. How would you tell it's a dinosaur? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
Hey there YouTube, the Dapper Dinosaur here. It is finally time for another Speculative Evolution update. I know these are not coming out as fast as a lot of you would like, but I am getting through it and we are getting close to the end of Phase 2. There is light at the end of the tunnel, but it's not quite done yet. However, we have 8 new organisms to go over today, so without further ado, let's get started. Alright, first up we have Actimisa. Actimisas are one of the first organisms to venture onto the shores of Almaisha. They are adapted for survival within the intertidal zone, being able to emerge from water for brief periods of time. They act as opportunistic scavengers, tracking down and feasting on the remains of marine organisms that have been washed ashore. An Actimisa is pictured here stopping for a rest in a shallow pool while traveling around a rocky shore. The internal gill cavity of the second tagma is capable of storing water, acting as a respiratory reservoir. Furthermore, the spiracles are now able to be clamped shut to prevent water loss when out of water. This allows the Actimisa to emerge from the ocean temporarily without suffocating. The skin is a leathery cuticle that resists desiccation when exposed to air at low tides and contains a high concentration of melanin to prevent radiation damage to the organism. The legs have been reinforced with stronger muscles and are capable of supporting the body when partially emerged from water. The feeding appendages of the first tagma have been heavily modified. The first pair of appendages have lengthened to become antennae used in scent detection, while the second pair are lined with radula-like keratinous projections for rasping carrion. Instead of broadcast spawning, Actimisas mate by locking their heads together in a gono-oral kiss, exchanging gametes directly from the reproductive chamber. The female acts as the recipient of sperm for the male, who will then lay fertilized eggs in the sediment at the lower intertidal zone. Actimisas are found most commonly in the intertidal zones, where they are safe from larger predators. However, their fundamental niche encompasses the seabeds of warm, shallow water, only being excluded from deeper habitats by the presence of predators and competition. They are scavenging detrivores, feeding on the carrion of other beached organisms. When actively foraging, they use their legs to wander across the coastlines and track down any fresh carrion. Otherwise, they will lower their metabolism by burying themselves under the sediment within the intertidal zone and entering hibernation. The second pair of arms of the first tagma are lined with multiple rows of serrated teeth, specialized for scraping flesh and carrion. The arms then manipulate chunks of flesh into the oral cavity for digestion. Since Actimisas lack a through gut, they must eject food from their stomach through their mouths before feeding. They have colonized the shorelines of Yama as well as the northern coast of Natash, which are coastal areas with sufficient warmth and intense light. The 4 eyes are evenly distributed around the first tagma to provide near 360-degree vision, but due to low resolution they are unable to distinguish potential carrion from predators. Rather, they rely on their antennas as the main sensory input. The chemoreceptors of antennae can detect trace scents both in air and in water, and are able to determine strength, direction, and type of sense. The chemoreceptors are so sensitive that an Actimisa can detect carrion from up to 2 kilometers away. Genetic ancestor, Diomisa. Scientific name, Litorambulo tenebrio. Origin, Paleotagmata. Lifespan, 5 local years. Average length, 5 centimeters from antenna tip to posterior end. And creature design, by Squidum. Next up, we have Bobber. Bobber is a placid herbivore that likes to spend time hiding in tide pools at low tide, emerging at high tide to feed. Here it is descending down away from the shore at high tide, startling a Longakura in the process. The bobber has feeding tendrils, which are retractable. The bobber's head is sloped down with its mouth now pointing directly to the ground. Its eyes have evolved retractable eye stalks, and it can barely make out objects, which helps it guide it towards its food or see incoming threats. It retracts its limbs laterally, making it seem like a small disc when threatened. Hardened plates on its skin serve as armor and cover most of the exposed skin when it assumes this position. Its eyes, feelers, and tail retract while in this position as well. If for some reason the tide pool were to dry out, the bobber can survive for up to a few hours in its defensive pose, as the plates help it retain a bit of moisture. Plates similar to the ones in its skin have developed on the sides of its mouth to help it break plant matter. Unlike their ancestors, bobbers no longer wrestle to reproduce. They now broadcast spawn if they have enough nutrients at times when the tide is high. They have 2 sexes, but little sexual dimorphism, males being only marginally smaller than females. Bobbers are herbivorous and are some of the largest animals in their habitat. While they prefer small sproutlings of Bossio magna when they can find them, this is rare. Instead, they mostly subsist on the tough leaves of wart melons. Bobbers have decent eyesight and can detect predators at a reasonable distance away, although by keeping to tide pools when they can, and being bigger than most things in said tide pools, they keep the risk of predation to a minimum. Genetic ancestors, Bobbird. Scientific name, Porcus armus. Origin ancestry, Pseudotetrapoda. Average height, 10 centimeters. Average length, 15 centimeters. Creature design, by Zord. Now we come to the Gulper. The Gulper is a pelagic filter feeder and occasional predator of smaller nectonic organisms. A trio here are seen feeding about 2 meters from the surface in the tropical midday sun of Almaisha. Descended from Xenocarrots, the Gulper has adapted to eat plankton and small organisms. While ancestrally limited to filter feeding, the Gulper's size allowed them to start eating small creatures as well. The anteriormost segment has reduced propulsive fins, although the creature exhibits little cephalization. The 3 segments posterior to the head segment have greatly enlarged propulsive fins. The rest of the segments still have vestigial fins that are little more than bumps. Its first segment eyes have evolved forward, while the ones up to the 4th segment remain the same. From the 5th segment, it lost all of its eyes until its penultimate segment, where it kept a pair. The last segment does not have a pair. The oral cavity takes up the space of the first 4 segments and opens up to a diameter of about 14 centimeters when feeding. The Gulper may close its mouth to gain more speed when following a small creature. The Gulper can rapidly open its mouth, creating a relative vacuum which can suck in prey and plankton. The oral cavity includes gold-colored bristles that trap plankton. Muscular action then pushes this food farther down the digestive tract. When moving the propulsive fins forward, muscles in the fins relax, allowing the fins to fold in on themselves, reducing drag. When they are moved back, the muscles tense, pulling the fins into a flat fan-shaped structure, maximizing the water that can be pushed against. Gulpers have male and female sexes. When they are ready to mate, a pair of Gulpers will touch anuses and stimulate them to release gametes, simultaneously ensuring a large number get fertilized. Oftentimes they eat their young as they grow into adult Gulpers. They can be found anywhere but Arctic waters and don't venture too close to shore. Genetic ancestor, Xenocarrots. Scientific name, Kirby aurum. Ancestry, Xenostigmata. Average height, 15 centimeters. Average length, 71 centimeters. Creature design, by Zord. Now we have Longakura. Longakura is a crab-like carnivorous descendant of Carulicanus porcus, found in warm tidal habitats. It feeds mainly on Diamisa minospina and any other small creatures less than 4 centimeters. It is also known to supplement its diet with small pieces of photosynthetic plants. It's similar in some ways to its bowbird ancestor, but Longakura has changed quite a lot in the past 10 million years. Pictured here, a Longakura attacks a lore tub at high tide around sunrise. Longakura has 4 main appendages used for walking across the seabed, and 3 jaw-like protrusions used for consumption. Longakura has no skeletal system and purely relies on muscle mass and blood pumping systems to move its legs. It has an open circulatory system, but also has small circular muscles at the beginning of each of its limbs to constrict blood flow and expand them, as well as simple smooth muscles throughout its body and limbs. The antenna-like protrusion on its back is mainly used as a secondary gas exchange organ. The creature pumps blood into it to regulate oxygenation in its body. Additionally, it can serve as a location for extra blood to be stored, which is necessary since blood pressure is one of the main ways the limbs are moved. It can also be used as a sexual display, and as a way to distinguish one species amongst closely related species. This structure is called a villus. Longakura's footpads are covered in small fleshy hairs that are used to help it stick to the sides of photosynthetic plants, as well as a sticky mucus substance that excretes from its footpads. Its front 2 jaw protrusions are used to feel the surrounding environment and to pick up small prey. It also uses its snout as a sort of thumb to help stabilize its 2 jaw protrusions. Its 2 chemoreceptors on each side of the snout can smell things like decomposing tissues, other members of its species, and even some predators. The horizontal gas exchange structures take oxygen from the water to the bloodstream by waving the tail up and down. Longakura, unlike their ancestors, only have 2 gonads, 1 female and 1 male. Once sexual maturity has been reached, usually around the age of 3 local years, Longakura will start searching for a mate, which will usually be the first of its species it encounters. Dominance between mates, and on rare occasions rivals, is demonstrated by an opening of the mouth parts and locking them together with the opponents. Once dominance is established, the less dominant Longakura will lay a membranous egg sac containing 10 to 50 eggs, which will be fertilized by the dominant Longakura. Longakura start out as small plankton-sized creatures, about 0.2 centimeters in size, with a simple flagellum for locomotion, that is also used as the breathing apparatus. They eat mostly tiny particulates in the water and on the seafloor. At around 0.2 local years of age, they lose most function in the flagellum, and their fins start to work as simple legs for walking on the seafloor. Between then and sexual maturity, they mostly just graze the seafloor until large enough to swallow larger prey. Longakura is found in the tidal and neritic zones of Almaisha's oceans. They stay in areas where prey is abundant and waters are warm. They also go into small caves or crevasses in rocks to mate and lay eggs. Genetic ancestor? Bowbird. Scientific name? Crusperi longakura. Origin? Pseudotetrapoda. Average height? 4.5 centimeters. Creature design by Ben Fiction. A lore tub searches for some food at high tide shortly after sunrise. Clearly displayed are the hardened skinned shell as well as various other areas of the skin that are tougher than others. seen as brown patches, while softer parts show the underlying blue tissue. The intertidal zone is a place that is not friendly to many creatures. However, the lore tub has managed to eke out a place under the burning sun. A proto-shell made of hardened skin is located on the dorsal surface of the creature, while its spiracles have changed so to function with water as well as with water vapor, allowing the animal to go on land when it has recently rained or when it is very humid. The shell has an interesting coloring of red and green. The reason for this is that the earliest Diomisa with shells evolved pigments to camouflage against the green plant grows. However, as their shells got stronger and the proto-lore tub got bigger, the shell eventually became less of a camouflage tool and more of a mating display, where the ones with the brightest, most diverse patterns on their shells got more chances to mate. Somewhere along the line, a lore tub mutated a red pigment that showed up as well as the green pigment. This lore tub mated several times, and ones with no red pigment died out, creating the red-green shells of the lore tubs today. The two pairs of appendages on the cephalon of the lore tub have changed dramatically from its Diomisa ancestor. One pair has become like a moving spike, allowing the lore tub to rip and tear through carrion and cut up the thin stems of Bossio. This evolved after a certain fibrous protein found in the first appendage of the lore tub slowly grew harder and harder over time. This harder protein gradually got pushed to the top of the appendage, creating the spike we now see. The other has moved to the side and made sort of a cup, creating a shovel, useful for pushing things into the water and moving food into its mouth. It has also gained a reproductive appendage, although it is immobile and quite small. Essentially, the reproductive gland began to extend outwards, taking the flesh along with it. And now, while there is only one gonad, there are two fleshy bits that can dispel gametes underneath the head of the lore tub. A baiting strategy, facilitated by the use of reproductive appendages, has evolved in lore tub. A male lore tub will begin digging 2 holes in the ground using its spikes and shovels. After this is completed, the female that he has begun to court will deposit the eggs within the 2 holes. If her reproductive appendages don't fit or are too large, too bad for them. The male will do the same, depositing his gametes within. The male knows how wide his reproductive appendages are, and so he digs the holes to fit its size. This has caused a trend in both males and females to gravitate towards a similar size. After a while, the eggs begin to develop. These eggs will hatch, and the larvae are nearly microscopic. The ones that drift out to sea are never seen again, and the ones that stay on rocks and other such material, keeping in the intertidal zone and the shallows, live to grow big enough to mate, unless picked off by an adult lore tub or water hoppers. The cycle continues. Lore tub are primarily scavengers and secondarily herbivores, and are found most commonly in the intertidal zones where they don't get preyed upon by much larger creatures who would try to take their lives. They have adapted to life in the intertidal zone. They are detrivores, but if hungry, will not hesitate to go out into the shallows and cut up wart melons or spiral plants with their spiked appendages. While actively foraging, they use their legs to wander the coastlines and track down any fresh carrion. Otherwise, they will rest near various photosynthesizers so they can have an easy meal. They are most common around Cha Tang and southern Natash, although they are excluded from equatorial latitudes due to being too sensitive to overheating, despite their small size. The northern shore of Ras El Khalb has a small population of lore tub, but they are growing exponentially, although the Durospina and Minospina continue to compete against them. The 4 eyes are focused in the front of the animal and grouped in 2s together. They have a lid of sorts, or perhaps more properly, a brow. The front eyes are better adapted at seeing out of water, having a deformable lens, but the back eyes, while they are useful, have low resolution. This has resulted in the behavior of a lore tub to move away from anything that is bigger than it and moving, unless they can sense it is another of its kind, and it is mating season. However, if they turn their front eyes around to look at the target, they may continue to run or begin to move hungrily towards the prey/carrion. The chemoreceptors of the antenna have decreased on their spiked appendages, having a limited range of about 60 centimeters. The shovel-like appendages are better, gathering sensory details from about 5 meters away. The shovel appendages are very touch-sensitive. Genetic ancestors? Diomisa. Scientific name? Lorem ipsum. Ancestry? Xenotagmata. Average height? 1.9 centimeters. Average length? 5 centimeters. Creature design by Smongak. I'm not sure if I'm pronouncing that right. And now we're on to our first Stephanozoan from Phase 2, the Rose Comet. Rose comets are tiny parasitic organisms who are on the cusp between being planktonic and nectonic on Almaisha 470 million years ago. They swim with their mouths facing forward, propelled by their flagella-like mode of tentacles. They can latch onto much larger organisms and begin rasping away bits of flesh. Pictured are 2 rose comets, one attaching itself to a cage-gill worm, the other having detached, well-fed, and off to digest its meal. The belly and stomach of these rose comets have become larger than its ancestors. To support the larger body, rose comets now possess a pseudocole to facilitate transport of gas and nutrients. Motive tentacles have lengthened and flattened to be more efficient for swimming towards hosts. The flat surface of the motive tentacles also serves as a secondary function as a gas exchange site, although there is no circulatory system to distribute the gases efficiently. The feeding tentacles have been modified for the purpose of latching onto larger organisms, and will henceforth be referred to as anchor tentacles. Each anchor tentacle is lined with chemoreceptors and mucus-secreting glands, with the latter being most abundant towards the distal tips to facilitate adhesion to the host's skin. The jaw tentacles have become more thick and stout, with serrations resembling a snail's radula lining the medial side. Rose comets appear translucent with rose-tinted coloration. Rose comets are now capable of parthenogenesis by self-fertilizing their ova, producing genetically identical daughters. However, unrelated individuals may still mate together in a similar fashion to their ancestors, meeting mouth-to-mouth then releasing their gametes simultaneously. The fertilized eggs are left to drift with the zooplankton. As part of the zooplankton fauna, rose comets are prey to a variety of small organisms, as well as larger filter feeders. However, the tables are turned when they manage to latch onto a host, some of which can be orders of magnitude larger than the parasite itself. Common hosts include phytopinnipeds, protomycinids, and durospinas. They are capable of swimming against the currents to a limited degree, but only do so when in close proximity to a host. The distal tip of the anchors are covered in a thick layer of mucus in order to adhere to the host organism's skin. Upon successful landing, the jaw tentacles begin rasping away at the host skin, shoveling morsels of flesh into the stomach cavity. A mixture of enzymes and anticoagulants are secreted through the stomach to facilitate breakdown of the host tissue. A fully fed rose comet may survive without food for up to 50 local days. They are found worldwide, most abundantly in warm oceans around the equator. They are currently found only within the epipelagic zone in coastal areas and open waters. Their only sensory input comes from the chemoreceptors on their anchor tentacles, providing smell and touch. These direct rose comets towards hosts and trigger the rasping response when the anchor tentacle has attached to a suitable host. Genetic ancestors, rose crown. Scientific name, Stephanoflagellata rosiae. Ancestry, Stephanozoa. Lifespan, 200 local days. Average length, 0.5 cm bell length, 2 cm mode of tentacles. Creature design, by Squidum. Next is the Xenocarrots. Xenocarrots are small shrimp-like organisms that serve as generalists in a variety of habitats. Different species exist in different sizes and colors, better suited to different habitats, but beyond that, their general morphology remains unchanged. Xenocarrot agilis thrives among sandy sediments as a scavenger, picking up retinal phytes, carrion, and the occasional small prey from the seabed with their feeding appendages. Their mandibles at the base of the head allows them to consume a wide range of foods. They are highly maneuverable and moderately fast, suitable for escaping large predators in compensation for lack of protective armor. Here, two Xenocarrots are pictured swimming around each other, perhaps preparing to mate. This clade of Xenosegmatans first arose when a descendant of Xenoeulicurbi developed tagmosis of the first 3 and last 2 segments, dividing the body into distinct head, abdomen, tail regions. The head possesses 3 pairs of feeding appendages, modified from swimming appendages, and 3 pairs of mandibles, modified from gill fronds. The mandibles are serrated with reinforced keratin. 3 pairs of compound eyes sit atop the head, with the front 2 pairs being the most well-developed and facing the front. The head contains a relatively dense network of ganglia compared to the other segments, forming a primitive brain-like organ. Each segment of the abdomen contains a pair of large swimming flippers, with the gill frond sitting underneath each flipper. Flippers move in an undulating unison along the abdomen, swimming in a similar fashion to a normal charis. Motion of the flipper during swimming pushes water through the gill, increasing efficiency in oxygen uptake. Each segment has retained a pair of reduced dorsal eyes. The lengthened abdomen houses a lengthened digestive tract and a simple stomach for each abdominal segment. As sequential hermaphrodites, Xenocarrots can simply morph into the other sex whenever there is an imbalance in the sex in the current population. The gill fronds of the tail are modified into gonopods, which males and females use to latch onto each other during copulation. The male sits on top of the female and both release their gametes simultaneously in such close proximity to increase fertilization success. This produces a large number of fertilized eggs per successful mating attempt, which are left to float among the zooplankton until they drift down to the sediment. Xenocarrots are generalist omnivores, having access to a great dietary range due to their highly adaptable mandibles. As opportunists, they forage in the shallow waters for potential meals, searching for retinal phyte matter as well as carrion and small prey. Feeding appendages grab onto the food and then bring it to the mandibles. The mandibles chew up the food into chunks, which are then manipulated into the mouth. They can be found in all shallow waters of tropical to temperate warmth, present anywhere with moderate biodiversity. The compound eyes of the head can distinguish size, shape, and color of objects. Due to the arrangement of eyes on the head, depth perception is achieved to some extent. Abdominal eye spots can only be used to distinguish shadows or time of day. Genetic ancestors: Xenoeulicurbi. Scientific name: Xenocarrot agilis. Origin, Xenosegmenta. Lifespan, 4 local years. Average length, 10 centimeters. Creature design by Squidum. And last, we have Igrina. Igrina is a burrowing organism that spends most of its life tunneling through the sediment. They consume scraps of organic matter sunken into the sediment, as well as the sediment itself. Pictured here, a Igrina emerges from the sediment after being disturbed by something. Due to the tunneling lifestyle of Igrina, the eyes of each segment have diminished in size due to atrophy. The mouth has developed sideways closing jaws. This is homologous to the mandibles of Ipresi. The muscles that extend into the appendages of Ipresi have remained embedded around the mouth in Igrina, allowing controlled opening and closing of the mouth. Hundreds of tiny chemoreceptor pores surround the mouth and the front of the head. Across all segments, the swimming limbs and gilfrons now align laterally to the body. The swimming limbs have become thinner as they are now primarily used to move along the sediment. The gilfrons continuously beat back and forth to get a continuous stream of oxygen while aiding in burrowing. The last segment has lost its eyes and gilfrons entirely. The swimming appendages of the last segment face towards the posterior end. Igrina are true hermaphrodites. When two individuals meet, they will twirl together while simultaneously releasing gametes. This occurs while both partners are underground. Fertilized eggs are left to develop and hatch in the sediment. Igrina lives on sandy beaches, acting as a detrivore. They consume clumps of sediment and bits of organic matter. They tunnel just beneath the seabed to feed on sediment, occasionally surfacing to feed on scraps of detritus if any are detected above. The jaw grabs and shovels clumps of sediment and detritus into the mouth, carving out a trench or tunnel in the process. The food is digested as it traverses the intestinal tract, passing inorganic or indigestible material out the posterior end. They are found in all shallow water at all latitudes except the polar regions. They can be found on continental shelves and slopes as deep as the bathypelagic zone. The eyes are vestigial, only capable of distinguishing light from dark. They would only be useful for detecting whether the organism is currently buried. On the other hand, the chemoreceptors around the mouth are sensitive and finely tuned, able to guide the creature towards rich nutrients. This allows Igrina to locate a food or mate, despite being virtually blind. Genetic ancestors, Xenuyuli Kirby. Scientific name, Diminotoculi Igrina. Origin, Xenosegmenta. Lifespan, 4 local years. Average length, 7 centimeters. Creature design by Squidum. Well, that's it for this update. At the time of this recording, there are currently 37 entries for Phase 2 on the Speculative Evolution page on the World Anvil. That's crazy to me. I thought that maybe I would get a couple dozen at most, but we're still not over yet. So stay tuned here on this channel, and make sure to like and subscribe if you haven't already. Thanks for watching. But before you go, I'd like to give a special shout out to all my channel members and my patrons on Patreon, especially the $20 and above patrons and members. Benthoven, Ian Chen, Chris Love, Henry Hutanen, and Bob Knob. Your support allows me to keep making these videos, and without it, I would have to stop. If you're not already a channel member or a patron, there are links in the description for how to join either on YouTube or on Patreon if you like. But if a monthly donation isn't right for you but you'd still like to help out, there are a number of ways you can do so. First, every like, share, and comment on any of my videos really helps me out with the algorithm. And second, if you'd like a more concrete and monetary way to help out, there is a merch store linked in the description as well as an Amazon wishlist. I'm the Dapper Dinosaur.
You found the skeleton. How would you tell it's a dinosaur? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on this.